hello. Welcome to an adventure. I will get that one of these days. I hope that you can hear me all. I hope that you're having a good day. Welcome, Hannah. I see you there in the chat. Welcome, everybody else who's here. Do let me know if you are able to hear me or if you are not able to hear me. That would be lovely. Took just a couple of extra moments to get set up today because the room was used for something else. And so I had a little extra setup to do, but hopefully everybody is good. Tie-dye Huntress, thank you very much for letting me know. All right. Yeah, welcome everybody. In case you're new here, I am Anthony Wright de Hernandez, Community Collections Archivist here at Virginia Tech, and this is a once weekly show where we kind of do an unboxing of archival materials. So most often they are materials or collections that I have never looked in before, and we just kind of see what's there together live, and usually we learn something. So the focus today, we're actually revisiting a collection that I looked at before that I knew had this topic in it, but that we ran out of time and didn't get to this topic. So we're going to the Paul Hill collection, and we will be focusing on the topic of interstellar flight. The reason we didn't get to interstellar flight last time that we looked at the Paul Hill collection is because there was too much good stuff about space stations. So we got so wrapped up in looking at the space station stuff that we never even got a chance to look at the interstellar flight stuff. So yeah, and Detective said, yeah, the microphone has just one job. It's supposed to make my voice be heard. I'm actually gonna try and put this behind me because I'm moving my head around and I'm like, I bet they can hear that over the microphone. We'll see, it's fine. It's not like the audio setup is the same week to week. In fact, it's not like the audio setup is the same week to week. Eventually, I am working towards setting this up in a place where other people don't use the space and I can just set it up and leave it instead of having to tear it down after the episode every week. Anyway, before we dive in to looking at some history from NASA, we're going to look at a brief statement about the history of Virginia Tech. We do this every episode, so it's just important to pay attention to this history. Virginia Tech acknowledges that we live and work on the Tutelo and Monacan people's homeland, and we recognize their continued relationships with their lands and waterways. We further acknowledge that the Morrill Land Grant College Act of 1862 enabled the Commonwealth of Virginia to finance and found Virginia Tech through the forced removal of Native nations from their lands in Western territories. We understand that honoring Native peoples without explicit material commitments falls short of our institutional responsibilities. Through sustained, transparent, and meaningful engagement with the Tutelo and Monacan peoples and other Native nations, we commit to changing the trajectory of Virginia Tech's history by increasing Indigenous student, staff, and faculty recruitment and retention, diversifying course offerings, and meeting the growing needs of all Virginia tribes and supporting their sovereignty. Virginia Tech acknowledges that its Blacksburg campus sits partly on land that was previously the site of the Smithfield and Solitude plantations, owned by members of the Preston family. Between the 1770s and the 1860s, the Prestons and other local white families that owned parcels of what became Virginia Tech also owned hundreds of enslaved people. We acknowledge that enslaved Black people generated wealth that financed the predecessor institution to Virginia Tech, the Preston and Olin Institute. And they also worked on construction of its building. Not until 1953, however, was the first Black student permitted to enroll. Through inclusive VT, the institutional and individual commitment to prosim that I may serve, in the spirit of community, diversity, and excellence, we commit to advancing a more diverse, equitable, and inclusive community. I don't think we can delve into history without paying attention to the institution's history. So I like to just make sure that we look at that before we move forward and keep it fresh in mind. All right, so today the Paul R. Hill collection. The whole collection spans 1936 to 1996. The materials that I specifically pulled for today are only the materials in box 5, with the exception of one folder from box 1. And I should say the materials that my student assistant pulled for today, because this is yet another one that my wonderful student assistant Sterling prepared. So I know less than I do when I'm normally, less than when I prepare them myself. Every time you go through that, I'm amazed at the year people of color were allowed to attend. It just blows my mind. I don't understand why it took that long before they could attend. Institutional racism. I mean, the first, before I say this, I'm gonna pop up back over here. It's not mentioned in the statement on the left about the land acknowledgement, but the first Indigenous student who was a member of the Monacan Nation graduated from Virginia Tech in 2010. So, yeah. There were other Indigenous students that graduated before then, but the first one from the actual nation whose lands the building sits, lands the campus sits upon, wasn't until 2010. Women could vote long before people of color could attend this college. Indeed. And women could attend long before people of color could attend. 1953, it was still primarily a military institute, which may have had something to do with the late date, but really it was racism. I've never understood segregation anyway. They're people, not colors. Indeed. Yeah. Exploring some of that history is really, really interesting. We've looked at the institutional history of Virginia Tech a couple of times. If you go back, especially to the first year of episodes, the VODs are out on the library's YouTube. There are multiple episodes where we look at some of the timelines of history. I know there's one where we go through the Black history timeline specifically. I will say I stumbled over language a little bit more back then, but it is definitely interesting to kind of dive into those topics and understand when things happened and the challenges that even the people who were accepted. Like the first Black students to attend here were required to be in the Corps of Cadets, were not allowed to live in the Corps of Cadets barracks, had to live off campus, and the family that gave them a place to live was about a mile from campus, but they had to get up and walk to campus and still look just as fresh as the other cadets when they showed up for the morning drills. So they would walk to campus. There was no space for them to change in on campus, so they found somewhere and changed into their uniform, because they didn't walk here in their uniform, because then it would have been all sweaty instead of fresh and pressed the way that it needed to be at the start of their day. So yeah, lots of challenges. And we can definitely look into that a bit more if people are interested. I'm not opposed to covering that topic. It's just that usually people end up not being as interested in Virginia Tech history as some of the other things that we have. Today, as I said, we're looking at Paul Hill. This collection is relating to the NASA career of Paul R. Hill. so quickly. Who the heck is this person? I'm trying to make sure I can read from up there. Okay. Renowned NASA engineer and UFO enthusiast. He received his Bachelor of Science in Mechanical Engineering from the University of California, Berkeley in 1936. And after teaching at the Polytechnic College of Engineering in Oakland, California, he began his career with the National Advisory Committee of Aeronautics, NACA, in 1939, which later became the National Aeronautics and Space Administration, NASA, in 1958. He worked at NASA until 1970, where he published numerous scientific and technical reports. Yes, UFO enthusiast. This next paragraph here, he was also an adamant UFO enthusiast. Based on his own personal sightings in 1952, Mr. Hill tried to use his scientific and engineering knowledge to understand how UFOs worked, and eventually built his own flying platform, which we looked at that the last time that we looked at materials from this collection. He wrote a book on the topic, Unconventional Flying Objects, a Scientific Analysis, which was published posthumously in 1995. So he approached the topic of UFOs from a very scientific, analytical perspective, and his interest in the topic of UFOs led to or influenced some of his engineering and design work that he did for NASA, to the point where he built a flying platform that somebody could, it sort of like was like a disc that somebody could stand on that could fly. And we looked into that and looked at that the last time that we looked at his materials. And sadly, I do not have the box with those materials in it here today. At least I don't think so. I might. I have some photographs here, and it might be in the photos, so we can look if people want me to. But specifically, what I have today. Is box 5. So I have box 1, folder 8, specifically for this, the time required for interstellar travel. But otherwise I have box 5, where there are various folders talking about quantum theory, and basically, we're trying to approach his work on interstellar flight. You want to see the UFO spotting platform? I will see what I can find. So there are some various things in here about interstellar flight, and we're gonna try and I'm typing in the wrong keyboard. Again, I mean, this happens often. Let me see what I can, spotting platform? Was that mentioned in here? Because I don't, the flying platform, let me see what I've got. Which is honestly what this show is all about. It's just, let me see what I got. Because we've pulled a part of the collection. And like I said, I think we might have, in the photographs, something with the flying platform. And I don't mind starting there. Life Systems, Space Conference, Interstellar Flight Figure Originals, Long-Term Flight Panel Negatives, Slide Negatives, Photograph Negatives. Photographs. I'm pretty sure one of these photographs folders is going to have something about that flying platform. I just don't remember, because it has been a long time. You have one job, keyboard, exactly. It's been a long time since I really dove into the collection. I don't remember when we did the last episode. I think it was last year sometime. Let me see. What do we have? What do we have? This one is just photographs. So that's Mr. Paul Hill from 1981, it looks like. Oh, no, here's his flying platform. Yeah, we got this. Okay. This is an official NACA photograph here. I think this is the flying platform. And it's got the little helicopter blades. So, you see where I've got, oh yeah, here it is in use. Here is the flying platform in use, being tested by the National, I always forget what NACA stands for. National Advisory Committee on Aeronautics. The precursor to NASA. And so I don't know how well you can make it out. And why? Okay, the camera just wants to be really like fuzzy. It wants to fuzz in and out. It didn't used to do that, and I don't know why it started. But there might be better pictures, but basically there's a small platform strapped to this guy's feet, and that hose is connected into the platform, supplying the fuel. So he's starting off with just, how do I get something to fly and hover in place? And so basically this is a small hoverboard. And the guy's got a rig on so that he can't fall and hurt himself. He's attached to a harness on a rig, and the hoses are there. So it's not practical for actual use, but this is basically a hoverboard. Here you can see another view of somebody riding the hoverboard. We have another collection. I don't know. I don't think we came across why it wasn't developed further when we looked at it before, and I don't specifically know why. I know we have another collection where that we looked at on stream, and I'm trying to remember the name of the guy. I could find it in a minute. We have a collection from somebody who was working on a rocket pack, like if you've ever seen the movie The Rocketeer, like a jet pack that goes on somebody's back. That was under development for NASA as well. And we have a collection from the guy that was developing that. And I think ultimately it just ended up not being necessary or wasn't ultimately very practical. And I would assume that the same ended up being the case here, where it was useful to study and to build prototypes, and they learned things from it, but I guess I don't know. I would be curious to sort of dig into that and find out. But my impression is that it just ended up either being, for one reason or another, not logistically practical. Because it is a neat idea, and it is a very science fiction idea. And these are all official NACA photographs. I don't have the captions that go with them. All NASA photographs, and I don't know for certain about NACA. I know NASA photographs, when they're serial numbered like this, there's a caption that belongs with that photograph. I presume the same is the case here, but also these are confidential photographs, and usually the ones that I end up looking at were taken for press purposes. So it's possible these didn't have official captions with them. I don't know. It's also possible that in his reports and publications that there's more information about specifically that hovercraft development. I don't remember, because it's been a long time since we looked at it, and if I had the boxes with those here today, we could definitely look at it. I'm going to see what else we got, because these are a bunch of the same, just more of the same. All right, we got John Palmer, David Henderson, Paul Hartman, Paul Hill, and Thomas Kennedy. Ooh, there's a nice look at flying platform under development here. We got, this one is really similar to, like, if you turn it sideways and attach it to the back of a boat, it's like the motor that you use to travel through swamps down in Louisiana and Florida. I can't think of the actual name for that, but it's like just like a big propeller on the back, except that in this case, it's underneath. If anybody does remember from before and wants to remind me, that's good. Also, it's possible we didn't get into it because we were looking for this stuff last time. These are space station designs. Airboat, yes. Thank you, Titantress. Because yeah, last time we explored these space station designs, I can look specifically, because if there's enough material in this collection about the flying machine and specifically that sort of hovering device, if there's enough information in the collection about that that we didn't already cover in the other video, I could do another stream with this collection where we focus on that. I would just have to look. Combination of a large TV satellite antenna and a trampoline. Which, this one? Yeah, I would agree. All right. It's funny, I haven't started with the photos before. Oh, yeah, there we go. We'll do a couple more here just to look at the little flying platform stuff. But then I do want to get into interstellar flight, because that was the topic today specifically, that I actually brought the relevant folders. Oh yeah, like the NASA watch band is very thematic. So this is more of a, this we've moved on. So the previous items were under NASA or NACA, and now we're into NASA. This is a photograph from NASA, L681447, which sometimes you can do internet searches with those numbers and get the actual captions, but it's not reliable, or I would definitely try it. But yeah, this is a more, like, it's refined. The prototype is a bit more refined for demonstration purposes. I don't really quite understand what's happening in the photos, other than that he's in the thing and holding on to it. But I don't see, like, where's the, how's it, where's the mechanism? I don't get at this point, but they look like they're having fun. I think this, I think this is actually not, I think this is meant to demonstrate the balance necessary to stay on it. I don't think this is actually like the hovercraft thing like we were looking at before. I think this is a rig designed to demonstrate or test or get people to practice the balance necessary to keep the hovercraft upright. There I do. And so they're on this thing, but it sits on the ground, and then there's a single point in the center. And this bottom piece here is like curved underneath, like so that it will rock, and you have to balance on it. Feels like it would give you a good workout. I love this one. He is stock still, perfectly balanced, but he's there with his head down and a pipe in his mouth. I just... I don't know. It's a good photo. Yeah. I don't know if you can make it out. I can just barely make out on the construction horse here. It says Space Rocker, R-O-C-K-E-R. So yeah, it's what I was thinking it was. It rocks around to let them experience alterations in balance. There you can kind of see that little curved bottom. Oh, and look, they even let the women on. After all the photos. Finally! They've been women. They've just been on the side watching. But finally, a photo with one of them actually in the rig. Let's see. Looks like we have quite a few photographs of the space rocker. Here you can see a concept drawing of what they were working on developing there. So the combination of the hovercraft and the space rocker platform that we saw, the idea was that this would be a sort of like a hovercraft type vehicle that people could use to get around on the moon. And all of this because Paul Hill was a UFO enthusiast after having seen a UFO for himself in 1952. It's an interesting idea. Unfortunately, I do not know why it was abandoned. Why astronauts are not using hoverboards to get around the moon. Maybe they provided too much thrust and they would have launched them into orbit or launched them off the lunar surface. I don't know. Okay. I don't know if we have enough documents specifically about the development of that, or if we just have the photographs. If we do have documents, it's definitely something that it's something that we could revisit in a stream where I actually come prepared to look at that specifically. I just, this week, it wasn't the focus, and so that box didn't get pulled. The one that might actually have this material in it. Because this week, we're supposed to talk about interstellar flight. So what is interstellar flight? Great, I will make a note so that I know to explore whether there's enough to cover that. Words. I have words. They are in my brain. Give me 1 second. I'm going to adjust this camera because it's not quite where it's supposed to be and it's throwing me off. There. I have a guide on the table that shows me where I'm supposed to put things, but the camera moved and the guide was having me put things in the wrong spot. Okay. For me, it's really difficult to read that. It's very faint. Plus, it keeps wanting to do weird things with the autofocus. Anyway, subseries, manuscript and publications. The time required for interstellar travel. Unfortunately, this one is undated, so I don't know specifically when this paper happened, but sometime during his tenure at NACA or NASA, they were working on figuring out how to travel to other stellar systems. So let's see what this paper is all about. This is a paper on one of the facets of interstellar travel, the interstellar travel time. Time is generally cited as the prohibiting feature of such travel, sometimes cited as the apparent technical insurmountability of achieving an adequate propulsion system. An adequate propulsion system is defined as one which can propel the vehicle to speeds approaching light speed. It is shown that with an adequate propulsion system, the time required to travel to neighboring stars could be very modest. A parametric study is presented of the effect of interstellar distance, acceleration rate, and maximum velocity on the interstellar travel time, both for the stationary observer and the vehicle occupant to stars within 100 light years of the sun. It is found that the time recorded by a stationary observer would be approximated by the time it takes light to travel the same distance, while the elapsed time, the time recorded by a stationary observer, so somebody who's not traveling, would be approximated by the time it takes light to travel the same distance, while the elapsed time to the vehicle occupants could be reduced by half for a velocity 0.9 that of light, and by an order of magnitude for a velocity 0.999 that of light. It appears important to use accelerations not lower than the 1 to 2 gravities range, but gains in time in going above about 10 g are small. So you need to go at least 1 or 2 g's in acceleration And if you can reach 0.9 that of light speed, then the people on the ship would experience half the time as observers not on the ship. And that increases by orders of magnitude as you approach light speed. Interesting. I'm curious and want to know more. An envelope has been drawn to bound the mass ratios for all possible propulsion schemes for vehicles carrying their own energy stores. Such a curve represents a true limit to propulsion possibilities. The limits are found to be not very restrictive. Okay. I'm not going to read this entire paper, but I find the introduction to be useful. It looks like there's some illustrations and stuff later, and I'm curious about, it looks like some sort of memo or something attached at the end. A number of papers have been addressed to the technical feasibility of interstellar travel. For reference 1, for example. Reference 1? Now I'm curious. Explore with me. All right, page 25, 27. Ooh, list of symbols. It's funny how fun I find this kind of stuff when it's a really dry academic paper, but I think it's really neat because I find this subject matter really interesting. But I'm uncertain. Reference 1. I haven't found a list of references yet. I've got figures. Appendix. Ooh, definitions. Okay. Yes, I did just get excited about a section called definitions. That actually looks like a really interesting section that I probably want to look at. Yeah, I don't have... Well, whatever reference 1 is referring to, I don't seem to have in this folder. Anyway, these of necessity utilize the applicable relativistic equations of motion. In general, only example trips to the nearest stars are considered. The exception is referenced to by Eugene Sanger, who went to the opposite extreme of considering a trip across the known universe. In general, the references deal extensively with good reason because of the great... In general, the references deal extensively and with good reason because of the great technological difficulties involved with the technical aspects and parameters of the propulsion problem. Predictions for future interstellar travel range from the optimistic predictions of reference 2 to completely pessimistic, with a popularized middle-of-the-road view being what the times involved would with a popularized middle-of-the-road view being that the times involved would be so great that only the descendants of those beginning the trip would reach their destination. So generation ships, okay. Propulsion is the key to interstellar flight, just as it is the key to any travel. But we do not have the key. Neither do we know, nor even have very worthy convictions as to what the key may turn out to be. The negative ideas as to how man cannot reach the stars or even send a probe to the stars are very easy to establish. It has been established time and again along the lines expressed in the following paragraph. The assumption usually made with regard to the propulsion system is to take the goals of the most promising chemical and nuclear rockets undergoing research and development, and to assume that for the sake of generosity, that by some magic, the performance is improved by an order of magnitude. This gives jet velocities in the order of 100,000 feet per second. But even then, a trip to the closest star would take thousands of years. If we could improve conventional rockets by the seemingly hopeless amount of 2 orders of magnitude, it would still take hundreds of years to make the trip. An improvement of 4 orders of magnitude would be very interesting, and with 5, we would be in business. It really seems unreasonable for any device in the ordinary sense of a rocket, which expels a working fluid at high velocity, to be a satisfactory approach. Positive ions of ion rockets are so heavy as to amount to a working fluid. It might be possible to eject still smaller particles at high fractions of the velocity of light, but such a motor has not been conceived. Yet, it is often said that a rocket is the only possibility for space propulsion. The other method of arriving at a negative answer is by the now famous article by William Markowitz, reference 3. A photon rocket cannot be said to expel mass. It expels photons, which are massless electromagnetic waves. However, it takes a small mass rate to generate them, according to Einstein's well-known conversion formula. To operate on a satisfactorily effective principle of the photon rocket would use equal parts of positive and negative matter, which on annihilation converts to radiant energy. Matter and antimatter. Going boom. Converting to radiant energy. It's an antimatter drive. Very Star Trek. Free particles of negative matter have only recently been observed, and no one knows how to efficiently generate them, let alone collect, contain, and handle them in a process. Possibly this could be learned. The blow comes when one attempts to direct the radiation in a beam, or even in one general direction, which would do nearly as well. Assigned to the reflector whatever efficiency one can reasonably imagine in 1970, and the reflector will burn up if we set an acceleration of 1g as the goal. I think this reference to 1970 probably gives us a hint as to when this paper was prepared. So this sometime in the late 60s or 1970, I would presume, just based on that sentence. If there were some way to make the radiation inherently directional, or to make a reflector approach very close to 100% efficiency, the story would be different. Extremely advanced propulsion technology in relation to that available in the 20th century is the key to interstellar travel. Whether that key will ever be found is not known. Some people say that even with the desired propulsion, the stars are too far away to make a trip practical because of the time involved. Some of them are. The 2 difficulties generally discussed are then 1, we cannot build the motors, and 2, the times required are too great. However, it seems very important to keep our ideas straight on what the real problems are. There are 2 problems, or really only 1? The author considers it essential in answering such questions, or to any broad view of interstellar travel, to separate the possibilities from the practicalities, and to look at the basic possibilities first. The scope of this report is limited to the basic possibilities. Practicalities or technical feasibilities are definitely dated. The long-range predictions of engineers and scientists are notoriously conservative because major advancements in science and engineering have been revolutionary rather than evolutionary. Consider the contributions of Hertz, Goddard, and Einstein, for example. This report deals in the main with the problems that can be technically answered at this time. The questions answered are 1. For various maximum speeds of travel, acceleration, and distance, what are the times involved? And 2, ignoring the technological difficulties of propulsion development, what are the ideal mass ratios that probably cannot be exceeded? To make the first question quite clear, Figure 1, I have the figures, yay, is introduced as a preview with little qualification at this point. This is Figure 1. Velocity over velocity of light. Onboard elapsed time in years. So onboard elapsed time to the nearest star is a function of velocity, acceleration and deceleration at 2 gravities. So as you approach the speed of light, your time required shrinks. It would take 100 years with a velocity somewhere. Let's see. So this is 0.1. One, two, three, 5. Somewhere roughly 0.07 the speed of light. It would take about 100 years to the nearest star. But to get it to drop that down to 10 years, you're looking at more like 0.7 the speed of light. Hi, Stephen. Space is big indeed, yes. So yeah, at 0.7 the speed of light, roughly 10 years to the nearest star. That's a conceivable speed, or a conceivable time, while being a speed that we don't know how to achieve yet, I think, is... okay, so... with little qualification at this point to illustrate the answers being looked for, Figure 1 is a plot of the onboard time required to travel between Alpha Centauri and Earth. Starting from a standstill and accelerating at 2 gravities to the velocity indicated in the abscissae. That is a word I'm unfamiliar with, but okay. Then decelerating at the same rate when required in order to stop at the destination. Note, the uninhibited range of velocity examined. The trip time depends more on the velocity than might be imagined. The onboard trip time is 4,300 years at 0.001 this velocity over the speed of light, and 2.1 years at velocity over the speed of light equaling 0.974, obtained by accelerating halfway. Reaching the same maximum speed, velocity over speed of light equals 0.974, so 97.4% the speed of light, at an acceleration of 10 gravities. The corresponding trip time would be 14 months. The short time taken at high speed will be explained in the section entitled Analysis. The first part of the present paper is a parametric study of the time required for interstellar travel for trips to and from various stars up to the order of 100 light years distant. Consistent with the thought expressed in the preceding paragraphs, the approach considers the relativistic possibilities, addressing such questions as how much speed and acceleration performance is needed or desirable to keep elapsed times within reasonable bounds. The independent parameters studied include the ratio of the maximum vehicle velocity to the speed of light, velocity divided by speed of light, the acceleration of the vehicle in reaching that velocity, the interstellar distances to many neighboring stars, the reference papers typically assumed an acceleration of 1 Earth gravity for half the distance and -1 gravity for the remainder, making the maximum speed a dependent function of the distance, and the trip strongly slanted toward the normal daily, I think that's supposed to be just daily, the normal daily existence of man. In consideration of the importance of time in covering great distances, the range of acceleration investigated in the present paper is about 1 to over 100 gravities, and the range of acceleration over speed of light is from 0.9 to 0.99999. High range of acceleration investigated is justified on several grounds. 1, the first interstellar vehicles would probably be uncrewed probes, relatively insensitive to acceleration. This is a preliminary look to see where the payoffs might be. Compromises should be made with this information in hand. And although it is recognized that humankind's limits for long-term acceleration may lie somewhere between 1 and 10 gravities, such values will be found to be not far from optimum in some cases and a considerable compromise in others. This is one of the most engaging and interesting scientific papers that I have ever read, or academic papers that I've ever read. I don't know, I'm enjoying it. In passing, it is mentioned that to those who consider the possibility or probability that Earth might be visited by extraterrestrial intelligence from another star system, the transit time is a highly pertinent factor. The calculations are equally valid in either direction, as the relative velocity of neighboring stars has been assumed negligible with respect to vehicle velocity. The second part of the paper deals with the theoretical mass ratio of the vehicle to achieve various fractions of the velocity of light. The second part is not required for the validity of the first, but some notion about mass ratios tends to delineate the difficulty of the problem in obtaining high values of velocity over speed of light, and to put the first part in perspective. To appreciate this report, the reader must accept the axioms and implications of the special theory of relativity. To appreciate this report, the reader must accept the axioms and implications of the special theory of relativity, such as time dilation and mass increase as the speed of light is approached. No new theory is presented, but its use is somewhat different. Short, simple derivations are given so the reader can more easily see the reasons for the results. My man, the UFO enthusiast. Exactly, yeah, he's really good. Hi, Wannabe Sayuri. Yeah, we're talking about how to get to the nearest stars. Sounds like you were talking from Alpha Proxima. Wait, does the microphone sound weird? Is that what you mean? Or you're the first one to mention it if it is the case. But also, how appropriate. If it sounds like I'm talking from a different star system, this would be the appropriate episode for that, I guess. Information is given in several tables on the number, nature, and distribution of stars in our stellar neighborhood. An appendix is given which gives some current views or theories on stellar and planetary cosmology as a guide to the identification of stars most likely capable of supporting advanced life forms on the associated planets. It is assumed that such star systems will retain much interest with regard to any type of stellar exploration. I can move the microphone up. I don't know if that... Let me know if this is worse or better. Wow, I don't know if I want to dive all the way into the analysis because we're an hour in. But I was curious about the definitions section. That looked really interesting. Oh, here's the list of references. Oh! Hello, welcome, Whimsies. Hello and welcome, to Archival Adventures. It sounds like the mic is maxing out. Okay. Let me try. I'm peaking. Okay, thank you. Hopefully this is better. Let me know if it's still really bad. Yeah, I don't know, because anyway, yes. Welcome in, Raiders. Welcome in, 16-Bit Eric and Whimsies. I hope that the end of your stream was good. I hope that, see, I think you were playing Return to the Mines of Moria or something like that. I don't know. It looked fun. But yeah, welcome everybody to Archival Adventures. I am Anthony Wright Day Hernandez, otherwise known on the internet as Rogan27, and this is Archival Adventures. It is a once weekly show that I do where I share materials from the archives and special collections here at Virginia Tech. This week we are looking at the Paul Hill collection and exploring materials in this collection around the topic of interstellar flight. So learning how we might potentially go to the stars. Ooh, did we do a shout out for Eric? If you're not following 16-Bit Eric, you should follow 16-Bit Eric. Eric is a wonderful streamer who has an absolutely wonderful community. He often brings them by here on Wednesdays for the show. And so very much appreciate let me see. I don't know. Yeah, there we go. So yeah, if you're not already following Eric, I recommend give a follow to Eric. It's a good time. But yeah, hi Pretty Witchery. Welcome in all of the Raiders. Hi Lauren. Hi Blue Rooster. Yeah, so we were diving through this paper because who doesn't want to just read a paper? But honestly, it's been a good read so far. I'm not going to do the entire paper, but the title was The Time Required for Interstellar Travel. And it had mentioned references a couple of times, and I was like, I can't find the references. Hannah, I'm glad that it is a common occurrence for customers to come into your shop while I'm streaming, and that means that you end up not being around to do things like shouting people out. I think it's great that you end up getting customers when I'm streaming. Anyway, so the first, let's see, Paul Van Handel. Relativistic treatment of rocket kinematics and propulsion. I don't know. But those were the references that he kept mentioning. But there was a thing I want to look at. I don't want to dive into like the analysis. We did the introduction. The introduction was great, but I don't want to get bogged down in the analysis when there's other stuff for us to look at still. But we have a table of known stars within 5 parsecs. And we were able to figure out, despite the fact that the folder is marked as undated, it's marked as undated because there's no date listed on the paper. But reading through the introduction, it mentions 1970. And so this paper is probably in the late 60s or 1970 when it was written. So we have a table of known stars within 5 parsecs. The sun is within 5 parsecs. In case you didn't know, it's a star we know about. And then Alpha Centauri, and then Barnard's star. And then for you Star Trek enthusiasts, Wolf 359 is 4th closest. Wait, parsecs is a real space measurement and not something made up in Star Wars? Indeed, parsecs is a real space measurement. Do I have, I wonder if that's in the definitions. Because if not, I can get a definition. parallax. The parsec. It's in the definitions. Not of distance, though. Parsecants are measures of angle. Story girl, thank you. The parsec. Clearly, to an excellent approximation, because of small angles involved, the stellar distance is proportional to reciprocal of parallax. Astronomers avoid the need for conversion factors by using the reciprocal of parallax as the measure of distance, a contradiction of the words parallax and second. The resulting unit of distance is called the parsec. Parsecs equal 1 over pi, where pi is the seconds of arc. To convert to light years, the following conversion may be used. 1 parsec equals 3.26 light years. That is a difficult definition to parse. Parsing that parsec definition is difficult. Let me see if I can get a more general usage definition. Okay, so this is from Oxford Languages, according to the Google. A unit of distance used in astronomy equal to about 3.26 light years. 1 parsec corresponds to the distance at which the mean radius of the Earth's orbit hang on. I have to boost the size. I can't see the words. 1 parsec corresponds to the distance at which the mean radius of the Earth's orbit subtends an angle of 1 second of arc. Puts Star Wars into context. So, when you make the Kessel run in less than 12 parsecs, it's basically a shortcut. Exactly. And less than 12 parsecs, it's not, it is a unit of distance, but it is a calculation of distance in terms of speed of light. Like it's distance in terms of time required to travel. So yeah, doing it in less distance is the same as doing it in less time. Basically, yeah, if you're doing the Kessel run in less than 12 parsecs, you're cutting through somewhere that people don't normally go. That's the only way to do it. Parsec is if you draw a triangle where you and the sun are 2 points, and the third point is the nearest star. Yeah, if you're going at the same speed. If you're going faster, then you could do it in less parsecs. Yeah, the parsec is weird. Anyway, so yeah, Alpha Centauri being the closest that we knew about at the time of this thing, then Barnard's star, then Wolf 359, Luyten 7268, Lalande 21185. Neither of those two have I ever heard about before. Sirius, Ross 154, Ross 248, Epsilon Eridani, Ross 126, 61 Cygni, Luyten 7896 Procyon, Epsilon Indi, Sigma 2398, Groombridge 34, Tau Ceti. Some of these get mentioned a lot in science fiction, and like some of them, like Groombridge 34, I've never heard of. It's a little cool and a little terrifying that Wolf 359 is a real star. It's the fourth closest star to Earth. So when you're thinking about the Borg in Star Trek, and the big confrontation where they stop the Borg are trying to go and assimilate Earth, and the Federation fleet is decimated in a battle at Wolf 359, the Borg were at the fourth closest star to the sun when that happened. Great fun to visit these places in Elite Dangerous. I haven't played Elite Dangerous, so I don't know. But I'm really curious, like, what the heck is up with Groombridge 34? Why have I never heard of this? Groombridge 34 is a binary star system in the northern constellation of Andromeda. It was listed as entry number 34 in a catalog of circumpolar stars. Published posthumously in 1838 by British astronomer Stephen Groombridge. Based upon parallax measurements taken by the Gaia spacecraft, the system is located about 11.6 light years, or 3.6 parsecs from the sun. This positions the pair among the nearest stars to the solar system. My guess is they use the change in position of the star in the sky in winter versus summer, creating a very long triangle. That could be. Anyway, so yes, these are some of the known stars. For those who don't know, let's see, Wolf 359. Wow, there's some of the interesting first hits of a podcast. Wolf 359 is a red dwarf star located in the constellation Leo near the ecliptic. We've explored before what is meant by the ecliptic in the episode where we were looking at contributions to science by women in the 19th century or 18th century. I can't remember. It's been a little while, but that was interesting. At a distance of 7.86 light years, or 2.41 parsecs from Earth, it has an apparent magnitude of 13.54 and can only be seen with a large telescope. Wolf 359 is one of the nearest stars to the Sun, only the Alpha Centauri system, including Proxima Centauri, Barnard's star, and the brown dwarfs Lumen 16 and WISE 08550714 are known to be closer. Its proximity to Earth has led to its mention in several works of fiction. So actually, looking at this, it's number 4 on this list, but number 1 is the Sun. And numbers 2 and 3, Alpha Centauri and Barnard's star, are both in the Alpha Centauri system. So it's really the second closest system to Earth. Red Dwarf got your attention. It is a good show, Lauren. I haven't seen their new stuff, but I did enjoy Red Dwarf. F, G, and K stars of 6.25 visual magnitude and brighter, within 100 light years of the Sun. I do not know the specific characteristics of F, G, and K stars. I wonder if that will be explained. GS, number in Boss catalog, right ascension from first point of Aries. See, this is where things get complicated. The right ascension numbers here, right ascension from first point of Aries, which means they're calculating based on constellations, which, I mean, you have to have a measurement point somewhere, but the crossover between, you got to know your mythology and your general constellation knowledge from a certain cultural perspective to even do or understand this math. Like, if you were from a culture that didn't pay attention to Greek mythology and Greek constellations, like Greek and Greco-Roman like influence, you would have no idea what the heck Aries is or where in the sky it might be, let alone what the first point of Aries is, in order to figure out what they mean by right ascension. Yes, our star is a G-type star. Yes. Spectral type. The sun is a G2. Alpha Centauri is a G0, but there are multiple stars there. G0K5M5, I'm uncertain. The M5 Barnard star is an M5. Wolf 359 is an M6. So yeah, that information is there. I will find out for sure what they mean. The boss catalog. Do stars have boss fights? I don't know. I'm not 100% familiar with the boss catalog, so let's find out. I always learn. That's the whole point. Boss catalog. The boss general catalog. Also, I make heavy use of Wikipedia when looking up things for this program, because I'm not using them, I'm not looking them up for the purposes of like needing rigorous academic sources to use in citations for like a paper or something. I'm just looking them up because it's more like, I just need a quick, what is this thing? Give me a general primer. And Wikipedia is great as a starting point for learning about something. If you want to go further in depth, you can follow the citation links in Wikipedia to find authoritative sources. Exactly, Pretty Witchery. Wikipedia usually has good citations if one has to go deeper. If you look at number 18, you'll see a system I have included in short fiction about post-expansionist society, post-human expansion to the stars. Tau Ceti. Tau Ceti is a popular one when it comes to fiction. So Alpha Centauri, Barnard Star, Wolf 359, Sirius, Epsilon Eridani, 61 Cygni, Procyon, Epsilon Indi, Tau Ceti. Those are ones that I'm very familiar with from Altair. They show up in fiction quite often. Some of these others are names that I'm not as familiar with. Related to how sci-fi and memorable the name is, probably Pretty Witchery. Declination from the celestial equator, visual magnitude, absolute visual magnitude, spectral type. Okay, so, oh gosh, no, I was looking up the BOSS catalog because somebody asked. The BOSS General Catalog, sometimes General Catalog, is an astronomical catalog containing 33,342 stars. It was compiled by Benjamin Boss, who lived from 1880 to 1970, and published in the United States in 1936. Its original name was General Catalog of 33,342 stars, and it superseded the previous preliminary general catalog of 6,188 stars for the epic 1900, published in 1910 by Benjamin's father, Louis Boss. Lovely. The Wolf 359 probably has a nerdy reason, but it sure does sound like a great place to have a massive battle. I mean, I think a lot of people probably didn't know about Wolf 359 until Star Trek. I mean, and now it's just iconic because of it. Okay. Let's see. Star spectral types. Ooh, here we go. F-type stars, as mentioned here, are yellow-white, an example being Polaris. G-type stars are yellow stars, an example being Sol, or the sun. K-type stars are orange, and an example of that would be Arcturus. But yeah, so we have a table of various stars. I wanted to look at the definitions because the definitions seemed really interesting. Which is the weirdest sentence. I want to look at the definitions. They seem really fun. But also they seemed really fun. Okay, what is going on? Okay, Pretzel. You're supposed to only be playing things without lyrics. This is supposed to be instrumental. Anyway, we're just gonna move on. It wasn't a bad song, it's just it wasn't supposed to have lyrics. All right, so we've got a chart. Variation of observed velocity over the speed of light, and I don't really understand t prime over t with time. I would probably have to read the paper to understand, unless somebody else knows, but observed time parameter. And dimensionless? Onboard time rate over observed time rate. So this is charting the difference between the amount of time that it takes for the trip to an outside observer versus the people on the ship, I think. But as was discussed, as you approach 0.999 the speed of light, the amount of time it takes to the person traveling goes down, and the amount of time it takes to the people outside goes up. Well, no, stays the same. It's just, it takes less time to the person on the ship. Which, incidentally, is the time dilation effect that you see in something like Planet of the Apes. Spoilers. Planet of the Apes. They travel really fast in ship. They arrive somewhere. They think it's a new planet, but they actually just came back to Earth after traveling for a long time. Spoilers. Absolute visual... Spectral type and absolute visual magnitude. This is an interesting map. Hertzsprung-Russell diagram showing the stars of known parallax in the vicinity of the sun. Sorry, Lauren. I figure I'm probably okay given that the movie has been out more than 40 years now. But yeah. Anyway, it's a good illustration of time dilation, sort of, because the people on the ship barely aged. But Earth has progressed significantly. What is this? Color magnitude diagrams for 10 galactic clusters, black and the globular cluster M3. The age at which stars of various clusters leave the main sequence, I think is what it's supposed to be, is shown on the scale to the right. Absolute visual magnitude, color index, B through V. Stellar age in years. The age at which stars of various clusters. I'm not sure I understand this chart. I get what it's supposed to be showing, I just don't understand it. I would have to have somebody explain this one to me. If anybody does understand it, feel free to explain, because I'm not following. Color magnitude diagrams. Right, and color is here, and magnitude is here. 10 galactic clusters. And the globular cluster M3. The age at which stars of various clusters leave the main sequence is shown on the scale to the right. That's what I don't understand. Because if you've got an X and a Y axis, how do you have a second Y axis? I don't understand. Anyway, I'm gonna read the definitions instead. Those that maybe I will understand. Maybe. Thank you, Story Girl. Let's see. Stellar age is pretty straightforward, and visual magnitude would relate to the amount of light emitted by a star. Color index might be the amount of redshift given the B through V terms. So the color index is the stellar type. That scale is yeah, like the Earth or the Sol being yellow, a G-type star. But so the visual magnitude would relate to the stellar age. So they could be on the same scale, and that would be okay. Yeah, color index, that's the spectral class. Anyway, I'm going to read the definitions. Parallax. According to reference 4, I'm not going to dig through the papers to find reference 4 again, unless you need me to. You can rewind in the VOD, and reference 4 was shown on screen. The distance to the stars within about 300 light years of the Earth can be roughly but directly measured by triangulation using the diameter of the Earth's orbit about the Sun as a baseline. The angles involved are obtained by photographic methods. The motion of the Earth over a 6-month period causes an apparent shift of the star image relative to the image of more distant stars. This image shift, when converted to angle, seconds of arc are used, corresponds to the angle subtended at the star by the Earth at its orbit extremes. However, parallax is defined as half this total angle subtended in the measurement. Parallax, then, is the maximum angle in seconds subtended at the star between rays to the Sun and Earth. I need one of these words defined. I do not know what a subtended angle is, so this I need defined. Okay, in geometry, of a line, arc, or figure, form an angle. at a particular point when straight lines from its extremities are joined at that point. That, thank you, definition, for not really helping me. Okay. I'm gonna bring this up because for me, I needed the visual to understand what the heck were they saying. So I figure maybe somebody else needs the visual too. And I am not super good at maths and geometry, especially hard because I can't picture things in my head. So, having a graphic, super helpful. The fact that the graphic's behind my head, less helpful. Okay, in geometry, an angle is subtended by an arc, line segment, or any other section of a curve when its two rays pass through the endpoints of that arc. The line segment, or of that arc, line segment, or curve section. Conversely, the arc, line segment, or curve section confined within the rays of an angle is regarded as the corresponding subtension of that angle. It is also sometimes said that an arc is intercepted or enclosed by that angle. The precise meaning varies with context. Thank you for variable definitions. For example, one may speak of the angle subtended by an arc of a circle when the angle's vertex is the center of the circle. Lovely. That's super helpful. Not. Okay, so an angle subtended by the arc of C to D is this angle here that is highlighted in red. And so you've got the rays here, the line that goes from this point to D. It's the point at which, so the third point here that defines the angle, you connect C and D with straight lines. They meet at point A. And the angle subtended by the arc C to D is the angle formed by the two lines once you have connected them to their point here. The question, and so that is the angle from point A. You get a different angle if you subtend to a different point. I think I grasp it. Thank you, Wikipedia, for just pointing out that I can't quite grasp elementary geometry. By referring to this as elementary geometry. It's interesting. I learned. Anyway, okay, so parallax. The distance to the stars within about 300 light years of the Earth can be roughly but directly measured by triangulation using the diameter of the Earth's orbit about the Sun as a baseline. The angles involved are obtained by photographic methods. The motion of the Earth over a 6-month period causes an apparent shift of the star image relative to the image of much more distant stars. This image shift, when converted to angle using seconds of arc, corresponds to the angle subtended at the star by the Earth at its orbit extremes. So you take the Earth's orbit extremes, draw a straight line to the star, and that angle is the image shift. However, parallax is defined as half of that angle parallax then is the maximum angle in seconds subtended at the star between rays to the sun and Earth. So you take the star and draw a line from the star to the sun and a line from the star to the Earth at one of its orbit extremes. And that angle is the parallax. The angle, okay, I got it. Anyway, wow. By choosing the proper seasons of year for measurements, there is no need for a ray from the star to be perpendicular to the Earth's orbit plane. Several methods of estimating the distance to very distant stars are available. The estimated distance of the reference star is used to calculate its parallax relative to a star at infinity. This parallax is added to the uncorrected parallax to give absolute parallax. Yay! Oh. There's a reason why I'm an archivist and not someone who went into astronomy as a profession. I find it interesting, but oh my gosh, these maths are something that it would take a lot of time for me to learn. It is the corrected or absolute parallax that is usually given and represented by the symbol pi in tables such as those given in this report. Lovely. Hopefully some of you understood that better than I did. Parsec we read clearly to an excellent approximation because of the small angles involved. The stellar distance is proportional to reciprocal of parallax. Astronomers avoid the need for conversion factors by using the reciprocal of parallax as the measure of distance. Contraction of the words parallax and second, the resulting unit of distance is called the parsec. Parsec equals 1 over pi, where pi is in seconds of arc. To convert to light years, the following conversion, 1 parsec is 3.26 light years. See, that 1 parsec is 3.26 light years, so much more usable for me. But I appreciate that it's fully defined here. I just like the bottom line because the bottom line is comprehensible to my brain. Stellar magnitudes. According to standard texts on astronomy, reference 9, for example. Okay, fine. Reference 9 never showed on screen. I will find it. Reference 9, and the one that we were looking at just a minute ago pointed to reference 4. Thornton, Page, and Lou, Page. I know those names. Starlight, what it tells about the stars. This one is pointing to Robert H. Baker, Astronomy, 8th edition, 1964. According to standard texts on astronomy, reference 9 for example, 2 stars or other bodies are defined as having a visual magnitude difference of 1 if their brightness bears a ratio of 2.512. A difference of 5 magnitudes corresponds to a brightness ratio of 100. The magnitude varies in the sense opposite to the brightness, and the 0 of the scale is such as to give the brightest stars negative values. A series of stars in the vicinity of the North Celestial Pole, whose magnitudes have been measured with precision, have been chosen to serve as a standard against which all other magnitude determinations can be compared. These stars are known as the polar sequence. The brightness of a star in the visual spectrum of light is, of course, measured by sensitive photometers. The apparent brightness of a star on a photograph plate depends on the wavelengths to which the emulsion is sensitive and the filters used, and photographic magnitudes so determined would vary accordingly. For example, a high-temperature white or blue star would tend to have a lower magnitude as determined by a blue-sensitive plate than either a red-sensitive plate or a photometric determination at visual wavelengths. The blue photographic magnitude has great usefulness in stellar applications and has also been standardized by the polar sequence. I really love seeing all the typewritten stuff. I used a manual typewriter to bang out stories when I was a little Lauren, so like 10 in 1993. I do appreciate the typewritten, partly because it's so much faster to read. But yeah, this is typewritten rather than like just photocopied or printed. Well, I mean, this is a photocopy of a typewritten. I do like the typewriter stuff. Handwriting can sometimes be very difficult to read. I've been known to struggle in reading handwritten things on this program. I will again, I'm sure. The absolute magnitude is the visual magnitude corrected to a distance of 10 parsecs by the inverse square law. The absolute magnitude of the sun is about 4.8. Most of that just over my head. I would have to take so much time to parse that to really understand it. Which is partly I can read it or I can internalize it. But reading it out loud, I don't always hear or like fully internalize what I'm reading, which is fine. But that seemed rather dense and I'm not going to go through it again. Spectral classification. The stars are classified as to spectral type by means of adopted standards. The major classifications are designated by the letters O, B, A, F, G, K, M, with decimal subdivisions in each running from 0 to 9. So you could have like a G.4 or an O.7. See the scale of the abscissa of figure A1. We looked at A1. No, we looked at figure 1. This is A1. We did look at A1. This one is not steak sauce. This one is spectral type. It's still called A1. This is figure A1. Sorry. We do sometimes do food programming. Can't handwrite very well anymore. Like seeing handwritten letters. Handwritten letters, so the angle of handwriting has changed over the years, and just commonalities, like the letters turn really far sideways eventually, and depending on, like, sometimes they'll go one way or the other, and it can just be really difficult. And some people's handwriting just clicks and you can read it just fine, and some people's handwriting I will look at and it makes no sense to me, but then I will hand it to somebody else and they can read it without problems. It's just sometimes the shapes make sense to you and sometimes they don't. The standards specify the limits of the intensity value of characteristic elemental spectral lines, which in turn depend on temperature and to some degree on the size of the star. An equivalent means of classification is called the color index, which is numerically equal to algebraic difference of the blue photographic magnitude of the visual magnitude, B to V. The following table from chapter 12 of reference 9 gives the approximate stellar temperatures. O5 being 50,000 Kelvin, B0 being 25,000 Kelvin, B5 15,600 Kelvin, A0 11,000 Kelvin, A5 8,700 Kelvin, G0 6,000 Kelvin. That is Seoul, right? G0. I get a Christmas card from my grandma. Just smile and nod and thank her. I understand. Oh, sun is G2. Sorry, G2. So somewhere between the 5520 and the 6,000 Kelvin. The sun's location. Wait, oh no, cosmology. Is this still the definitions? It is, but we're running out of time. So let me, this is again, roughly like 1970. The existence of planets. According to reference 9, the current theory of the formation of stars by the turbulent breakup of condensing masses of gas suggests that planets are formed in a somewhat similar manner in a process that might be frequently repeated throughout the universe. Although planets on other star systems are not now visible in the telescope, their existence has long been demonstrable by the observed periodic motions of stars due to unseen companions. In 1938, Peter Van de Kamp started his search for unseen companions of the nearer stars. He spent most effort on Barnard's star because it is the closest star in the northern hemisphere. By 1963, he announced a planet-sized object in a long-period, highly elliptical orbit about this star. But with more refined work, he announced in 1969 that the supposed planet was really two planets rotating in the same sense in nearly circular orbits that lie in approximately the same orbit plane. One, about 0.8 as massive as Jupiter, orbits at about 2.7 AU, astronomical units, within a period of 12 years, and the other, slightly more massive than Jupiter, orbits at about 5 astronomical units with a period of 26 years. The following information on known planetary systems is mainly from reference 12, Proxima Centauri. The faint red companion of Alpha Centauri, itself a visual double, has a planet with a mass of 1.86 that of Jupiter. The single red main sequence star Lalande 21185, 8.1 light years distance, has a dark companion of about 10 times the mass of Jupiter, causing perturbations with a period of 1.14 years. The star 61 Cygni is a double with a period of 720 years and is perturbed by a mass of 0.08, that of the Sun, at a period of 4.8 years. About 10 of these superplanets have been discovered on nearby stars of diverse types. These, like I said, really old, these are out of date. So many more now than when this was written. Oh, I couldn't let you do the announcement about time is running out. Angular momentum of stars, habitability of planets, something to consider if you're planning to travel interstellarly, habitable zone. This is a really interesting paper. Dynamic stability of orbits. I like the summary here. The importance of stars with planets which are capable of supporting life is twofold. One, only the planets of such a star would offer a ready-made environment for man, not only highly interesting because of its life forms, but possibly suitable for colonization. And two, only from such a star and planet is it possible for advanced carbon-based life forms to develop, which might someday communicate with or someday even visit the Earth. The scientific engineers of another generation may therefore send out stellar probes or other communications to the yellow stars of the F, G, and K types, which bear a considerable resemblance to our Sun. Of particular interest are our nearest neighbors in this class, such as Alpha Centauri of types G4 and K1, Tau Ceti type G4, and Epsilon Eridani type K2. However, some checks on the orbit stability of possible planets in the habitable zones of multiple systems such as Alpha Centauri should be made. Words. I might have gotten excited by this paper. This paper is fun and interesting, and I've been having a lot of fun, and there were other folders that were relevant to the topic, but I might have gotten, I don't know, there was some sort of gravitational effect pulling me into this paper because it was interesting. I've been having fun with it. Not worried about that. I want to see. You started out too strong with this paper. It was just too good. No, Tie-Dye Huntress, this is what happens. This is what happens. I used to pull entire collections, and I would come across something that was really, really interesting, and we would spend the entire time looking at one document. And I'm not upset about that, because as I have tried to explain to people here at Virginia Tech, the whole point of this program is wonder. The whole point, the whole reason that I do any of this, the whole reason for this program to exist, for any of this, it's all about wonder. It's about finding something in the archives and just really getting to like explore it and see what is neat, what is fun, what is interesting. Learning is fun, and I like that this stream, we get to learn together. Half the time I don't know what the heck I'm looking at, and you all in the chat explain it to me. I think it's just a lot of fun. And so that's the whole point. It's all about the wonder of the experience of like, this stuff is sitting there on a shelf. There's a finding aid that says it exists. This one is like Interstellar Flight Figure Originals. So these are the originals of the graphics that were attached to that paper. And I don't know, you can sort of tell they're really see-through. There, that's a good. So these are the graphs where he was charting those graphs and whatnot, and then these ultimately got photocopied into that paper. And if you're looking into like, well, what the heck did people do? How did people put graphs in their paper before word processors? Well, this was how. And these are, I'm gonna have to put gloves on here. These are slides for an overhead slide projector. Specifically, like this one is trying to explore topics in traveling between the stars, I believe. Like this is one of them. Long-term flight panel negatives, yes. So problem areas for long-term flight. We're gonna be traveling to another star. What are the problems? Because this was being prepared for either NACA or NASA, depending on the date. I'm guessing based on when his paper was published, probably NASA. Crew health, biomedical problems, zero or partial gravity and re-entry stresses, psychological problems, subsystems, environmental control and life support, power systems, control systems, crew protection systems, crew conditioning equipment includes simulators, EEM and memory storage before use. I don't know what EEM is. I would have to dig to find that. But like, if you were, say, working on a piece of fiction, like writing a speculative fiction story, or working on a movie or a TV show or something, and you needed to know the kinds of things that were actually being considered by NASA when they first started thinking about what it would take to fly to another star. These slides were part of a presentation on that topic in that organization. They might not be especially like relevant to researching that specific topic today because the science has moved on. But if you're trying to do like a portrayal of what it was like at NASA when they were first touching on these things. This is excellent data for that. If you want to understand the history of space exploration, the thoughts, this guy and his encounter with a UFO in 1952 that inspired him developing what was essentially a hoverboard with the intent that it was going to be used on the moon as a way for astronauts to get around. That's part of the history. It didn't end up getting built. They came up with other methods, but it's really interesting. And I will look to see how much there is on the hoverboard, the flying machine thing specifically, and if there's enough, then we will definitely do an entire episode on that. I just haven't looked to see what documents there are for that. We glanced at photos earlier today. Short and long-term contributions. Test and evaluation in space station performance of, we looked at space station stuff on the last episode that we did for the Paul Hill collection. If you want to look at that one, the VOD is on the library's YouTube. Difficulty achieving high probability of mission success for planetary mission simulation, major systems reliability. So just thinking through, like, what could go wrong? What could go wrong? Well, just about everything. But what specifically? So that they could try and develop solutions or consider how to alleviate the problems to make it possible. Test durations, crew sizes and composition, experiments, weight, space power, crew rotation, resupply, data return. I find these like slide decks where I don't have the notes aren't super helpful, but at the same time, just knowing that these are the topics they were discussing, even without the specifics of what they were talking about, is interesting. Yeah, Castavris, I think it's fascinating, all of it. I enjoy it. We have some really interesting NASA-related collections, and I just love diving into them. Anyway, 4:37. I always hate ending this show because I always want to do more. I'm like, I didn't do enough. Yeah, okay. Let me find a picture. Ooh. What is this? Oh, it's one of his space station designs. Anyway, I have to wind us out. I have to bring the show to an end because I have to tear down some stuff and get out the door and, all those things that come at the end of the workday. Next week, for our Archival adventures, do I remember what we're doing? Oh, next week I have materials from WUVT, that is Virginia Tech's radio station. But what we're going to be doing with the WUVT materials is we're going to be exploring the emergency broadcast system. So if you are not in the United States, the emergency broadcast system was started in the early 1960s, and it is a cooperative network involving radio stations and television stations that were intended to be able to put out alerts to the public when necessary. It has evolved over time. There was actually during or just before an episode a couple of weeks ago, a test of the emergency alert network where they pushed out an alert to everybody's cell phones across the entire country. So we have materials from the first revision of the guidebook for the emergency broadcast system from 1967. And we're gonna explore some of the documentation and training materials that the radio station had to acquaint people with the emergency broadcast system, its purpose, how it was implemented at the radio station, etc. So that is what we're looking at next week. And then 2 weeks from today will be the final episode of 2023 because it's the last Wednesday that the university is open this year. And Archivist Kira will be joining me, and we will be looking at something food related. I think it might be Christmas cookies. I'm not certain. But we'll be doing something festive with food 2 weeks from today. So let me see here where we're gonna go. I haven't looked to see who's live and determine who we might raid today. Looks like Steven is on again with Dordogne. The Monterey Bay Aquarium is on with the Shark Cam. Those are our two normal places that we go. You're gonna raid over to the day job. Okay. I have other options that I could consider, but at the moment, these are the two that are usually on, that we usually go to. Would you prefer sharks or video games? Any thoughts? Sure, we will do Shark Cam this week. We're gonna raid on over to the Monterey Bay Aquarium. Their streams are lovely and calming, and they've got the Shark Cam on, so it's just an underwater scene. It's a good time. You can hang out, you can have good background noise while you do it. Why not both? I have in the past. But yeah, we're gonna pop on over to Monterey Bay Aquarium. Thank you all so much for joining me today. I hope that this was fun for you. I hope that I will see you again soon. And until I do, keep exploring history, everybody.